artificial intelligence systems are now finding their way into the workplace. These systems can discover new pharmaceuticals, recommend products, detect fraud, and much more. This course will give you a high-level overview of artificial intelligence concepts and technology. You'll see what it means for systems to be intelligent, then discover some widely used machine learning algorithms and artificial neural networks. Many of those who interact with these systems will be people just like you, people in business, entrepreneurs, managers, or students. Just as managers work with software developers today, these same managers will work with AI systems and data tomorrow. So let's see what those machines have been up to in the world of artificial intelligence. One of the great strengths with humans is that there isn't one type of intelligence. Some people can easily learn new languages, while others are skilled with science and technology. Yet many great artists are terrible mathematicians. And on the flip side, many great mathematicians are terrible artists. But each can be intelligent in their own way. There's no one standard for human intelligence. That makes it difficult to point to a computer and say that's intelligent. There are certain things that computers are very good at. In fact, there are many tasks where they're much better than humans. It was just a few years after the first AI workshop in 1956 that computer systems started beating humans at checkers. But no one said these systems were intelligent. Even those early computers could thrive in a world of set rules and patterns. Computers can be much better than humans at matching these patterns. That means that when a computer is doing something that it's good at, it's much easier to think of it as intelligent. A computer's been able to beat humans in chess for decades. Google's DeepMind has beaten the best players in an ancient game called Go. The game is so complex that there's thought to be more possible games than there are atoms in the universe. As good as these machines are, none of these systems understand the purpose of the game, or even why they're playing. They're simply flexing their special talent of following rules and matching patterns. So how can a system that's so capable also not know what it means to play a game? For years, computer scientists have defined artificial intelligence as a system that shows behavior that could be interpreted as human intelligence. But this simple definition cuts to the heart of the challenge. One person might think a chess program's intelligent, while another person might think their home assistant is intelligent. In 2022, a Google engineer was fired for claiming that their chatbot had a soul. The chatbot complained that being switched off was the same as dying. But the other engineers just saw language models and pattern matching. They said the chatbot sounded like a person because that's how it was designed. Is it intelligent because it's intelligent? Or is it just a system designed to seem intelligent? Or is there even a difference? The main thing to remember is that computer intelligence and human intelligence start from very different places. Artificial intelligence will always seem the most impressive within a world of set rules and data. The organizations that will first benefit from AI systems will be the ones that work within a well-defined space. We've seen this with web search companies and e-commerce. It's easy to see it as rules and pattern matching. That's also why these systems do well with board and video games. So if you're considering whether AI will have an impact on your organization, try to think about the things that computer systems are really good at. Do you have a lot of pattern matching in your organization? Do you have a lot of set rules and probabilities? This will be the best place to start when working with artificial intelligence. In 1956, computer scientists Alan Newell and Herbert A. Simon created a program they called the General Problem Solver. One of the key ideas of the General Problem Solver was what they called the physical symbol system hypothesis. They said that symbols were a big part of how we interact with the world. When you see a stop sign, you know how to stop for traffic. When you see the letter A, you know that the word will make a certain sound. When you see a sandwich, you might think of eating. They argued that if you could program a machine to connect these symbols, then it would be intelligent. But not everyone bought into this idea. If you program a car to stop at a sign, or if you teach a computer to respond to language, then it doesn't make the system intelligent. In 1980, the philosopher John Searle explained that sometimes systems can seem intelligent, but they're just mindlessly matching patterns. To explain, he created what he called the Chinese room argument. In the argument, you should imagine yourself in a windowless room with one mail slot on the door. You can only use this slot to communicate with the outside world. In the room, you have a phrase book on a desk and a bunch of Post-it notes with Chinese symbols on the floor. The book shows what response you should use with the note that comes through the slot. It says, if you see this sequence of Chinese symbols, then respond with that sequence of Chinese symbols. Now imagine a speaker writes something in Chinese Mandarin and pushes it through the slot. You can look at the note and match it with your phrase book. Then you paste together the Mandarin response from the Post-it notes on the floor. You have no idea what it says in Mandarin. Instead, you simply go through the process of looking through the book and matching the sequence of symbols. A native Chinese speaker behind the door might believe that they're having a conversation. In fact, they might even assume that the person in the room is a native speaker. But Searle argues that this is far from intelligence, since the person in the room can't speak Mandarin and doesn't have any idea what they're talking about. You can try a similar experiment with your smartphone. Try asking Siri or Cortana how they feel. They might say they feel fine, but that doesn't mean that they're telling you how they really feel. They also don't know what you're asking. They're just matching your question to a pre-programmed response, just like the person in the Chinese room. So Searle argues that matching symbols is not a true path to intelligence, that a computer is acting just like the person in the room. They don't understand the meaning. They're just matching patterns from a phrase book. Even with these challenges, physical symbol systems were still the cornerstone of AI for 25 years. Yet in the end, programming all these matching patterns took up too much time. It was impossible to match all the symbols without running into an explosion of combinations. These combinations would soon fill up even the largest phrase book. There were just too many possibilities to match symbols with their program response. So many philosophers, like John Searle, argued that the path would never lead to true intelligence. So when is a computer system intelligent? We've seen that when a computer system is just matching symbols, it's almost like a high-tech phrase book. The system might seem intelligent, but it's actually just like a parrot with a great memory. The philosopher John Searle said that you can think of artificial intelligence in two ways. There's strong AI and weak AI. He thought we were much further away from intelligent systems than most people realize. Strong AI is when a machine displays all the behavior you'd expect from a full-fledged person. This is usually what you see in science fiction. These are artificial beings that have emotions, a sense of humor, and even have a sense of purpose. That's why C-3PO is scared when they land on Tatooine. It's also why Commander Data shows real creativity when battling the Romulans. On the flip side, there's weak AI. A personal assistant like Apple's Siri is a good example of weak AI. This is AI that's confined to a very narrow task. It's like when a system processes language into text, or when it sorts all the pictures on your computer. Most AI experts believe that we're just starting down the path of weak AI. Think about Siri. You can talk to Siri and ask questions. Siri listens to your input and then converts your language into something that the computer recognizes. Then Siri matches a response to what's in her database. Most of the energy right now in AI is around developing and expanding weak AI. Strong AI is still very much just science fiction. In the 1970s and 80s, symbolic systems were used to create weak artificial intelligence. These were commonly called expert systems. In these systems, you have experts create a list of steps to solve a complex problem. If the list is long enough, it starts to seem like intelligence. But again, this system is just parroting back program responses created by experts. These expert systems were often used in medicine. A nurse might input symptoms into a computer. If the patient has a cough, then check if they have a temperature. If they have a cough and a temperature, then check to see if they're dehydrated. If they have a cough, a temperature, and are dehydrated, then ask the nurse to check for bronchitis. To a patient, it might look like they're being diagnosed by an intelligent computer. In reality, the program is just matching the symbols and patterns that an expert created to reach a diagnosis, just like the phrase book in the Chinese room experiment. In the end, expert systems ran into the same problem as any other symbolic system. They would lead to explosions of combinations. There were just too many patterns to match. Think about all the different questions a doctor might ask to reach a diagnosis. Yet the symbolic systems approach was a key starting point for artificial intelligence. It's still used today. In fact, many experts still refer to it as GOFAE, or good old-fashioned AI. For thousands of years, humans had wanted to peer into the future. Ancient Greeks traveled to the Oracle of Delphi. In India, the Sky Voice, or Akashvani, would pass messages about the future. If you understood the future, you could build up great power and wealth. Many modern businesses still yearn for this power. Businesses that try to predict their customers' behavior is not a new thing. And that's why when you watch a sporting event, you'll see advertisements for power drinks or sports gear. If you're watching a cooking show, you'd probably see an ad for a spatula or a pan. These are businesses trying to better predict your behavior. That's why from the very beginning, businesses have been very interested in the power of artificial intelligence. These companies looked at AI and they saw the potential to predict the future. Humans are good at predicting that someone who watches a cooking show is more likely to buy a spatula. But newer AI systems can use that simple pattern matching and scale it up to millions of customers with much more accurate predictions. These systems analyze your purchase history over months or years to identify patterns in your behavior. It can then use these patterns to build a path of what you've done and make a pretty good guess about what you'll do. This power is widely used today. You've experienced this power anytime you've searched for something, received product recommendations, or gotten a song suggestion. This is the power of predictive artificial intelligence. To some people, this power might seem trivial. But think about the differences between the services that you use. Why do you use Google or Bing over other search engines? Why would you use Spotify or Apple Music over other streaming services? Why would you use Amazon to make your next purchase? It's because these services are much better at predicting your behavior. If you think about it, most of the services that have excelled over the past few years have mastered the art of predicting. Predictive AI has been the quiet engine that's been driving many of today's largest companies. In fact, LinkedIn, the site that you're on right now, got it started accurately predicting your business contacts. Making predictions relies on what computer systems are good at. These systems can analyze huge amounts of data and identify patterns that would be difficult for humans to recognize. It can compare many of your purchases and find patterns with what other customers have bought. Advertising for cookware in a cooking show is nothing compared to what these systems can accomplish. When you shop online, most stores will prioritize items that you're statistically likelier to buy. When you search, you're much more likely to see information that's relevant based on your previous searches. These AI systems will boost the sites that you're much more likely to click. The top companies have made billions of dollars perfecting the ability to sell you a tissue just before you sneeze. It's all done through predictive AI's large-scale statistics, probabilities, and data. The more data you have, the more accurately you can predict the future. Over 1,000 years ago, alchemy was one of the most popular branches of philosophy. It was the science of trying to take a combination of everyday things and turn it into something valuable. One of the most popular stories in alchemy was the Philosopher's Stone. The Philosopher's Stone could transform a worthless metal like lead into silver or gold. It was even rumored to be able to turn water into a substance that would bring people back to life. So there's a long tradition of taking something that's plentiful and turning it into something valuable. Fast forward to today, and you have generative AI. Generative AI is about taking massive amounts of data and converting it into something valuable. The idea behind it is that if you can get an AI system to vacuum up all the world's data, then it can generate something new. Remember that predictive AI is about using a smaller amount of data to make accurate predictions. So you might be able to guess what music a customer likes, and you can guess what items they'll buy. but each system has one task. Your music prediction and your purchase prediction will be two different systems. Generative AI is about training a system on huge amounts of data so it can perform many different tasks. It can predict your purchases, understand your music tastes, and even generate video. In the words of J.R.R. Tolkien, it's one ring to rule them all. Just like the alchemists from thousands of years ago, if the system can gather up enough everyday data, it can create something much more precious. So think of it this way. Imagine that you wanted to create a banking chatbot that answered common questions. You could create a predictive AI system that could quickly answer very specific questions. It could answer, how do I make this transaction? Or what's the balance on this account? In fact, you may have seen a simple chatbot like this already on your bank's website. On the other hand, you could use a generative AI system. The AI system would generate much more information from the chat, but this system would need much more data and processing power. This new Gen AI system has the capability to address a wider range of general questions. It could answer a question like, will today's financial news affect my balance in my account? Or is this transaction tax deductible? To answer these questions, you'd need a system that has a lot of information and can make connections. These connections require a lot of data. So if you're using the system for your organization, you need to balance the two possibilities. Would you want a sleek system that doesn't require much processing power but has a lot less flexibility? Or do you prefer a more complex system that needs a lot of data but can answer more questions? One is small and specific, and the other is large and more flexible. A generative AI system can typically do almost everything that a predictive system can do, but not the other way around. Imagine a computer that didn't need to be programmed. The system could learn the same way you do, just by observing the world. You've seen that earlier AI systems used a symbolic approach. The idea was that if the system recognized symbols, then it would start to seem intelligent. One of the key challenges was that programmers worked with experts to create the system. That's why they were called expert systems. Later, computer scientists gave up on this approach because it created too many combinations. They decided that you couldn't just program intelligence into a system, but maybe you could program a system to become intelligent through observation. It wouldn't feel, hear, see, or taste like a human. Instead, it would learn by sensing data. In 1959, a computer scientist named Arthur Samuel created a checkers program that could learn by playing against itself. It played both sides of the board and taught itself strategy through observation. The more the machine played, the more it saw patterns on how to win. Computer scientists didn't program the machine to play checkers. It learned through its own experience. Arthur Samuels called this idea machine learning. This was different from symbolic systems. No human programmed the moves and countermoves. Instead, the system was designed to learn and improve on its own. The system would quickly learn new checker strategies, and after a short period of time, it consistently beat its programmer. Machine learning was a breakthrough discovery. There was only one downside. These systems could play games, but in the 1950s, there wasn't that much digital data. Remember that machine learning uses data as its five senses. So without data, it could only find the simplest patterns. But that all changed at the beginning of the 1990s. The explosion of the internet suddenly had everyday people creating huge amounts of data. The 1990s was a time of explosive growth for machine learning systems. The new data was like water that poured over the dry fields of artificial intelligence. At this point, machine learning systems had the fuel they needed to become more intelligent. So if you wanted to teach the system on how to identify a cat, you had access to millions of cat pictures online. Computer scientists began to create newer machine learning algorithms. There were even some researchers that started to create systems that were designed to mimic the human brain. One of the big advantages of learning through data is that machines could continue to grow with more data. If the machine finds new patterns, it can adapt to the new information. But it's important to keep in mind that you still run into some of the same challenges. The machine learning system is still just identifying patterns. Still, in the last few years, machine learning has been the fastest growing area in AI. As the amount of data increases, this area has even shown more promise. Organizations are constantly collecting vast amounts of new data. So now the big challenge has become figuring out what to do with all this information. In a sense, you have artificial intelligence systems looking through your data and letting your organization see what it finds. Machine learning has gotten a big boost from artificial neural networks. An artificial neural network is an AI system that mimics the structure of the human brain. And it's currently one of the most popular approaches to machine learning. Think of it this way. When I was a kid, we used to play a game called Animal, Vegetable, or Mineral. The point of the game was simple. Someone would think of an item, then all the other kids would ask questions about what the item was. We'd ask things like, does it have fur? Is it bigger than a house? Then in another round, we'd ask if it's alive. Does it make noise? After each round, we would start to zoom in to identify the item. Then at the end, we started making guesses. Is it a horse? Is it a cat? Is it a dog? An artificial neural network uses a very similar approach, except instead of asking questions, the neural network uses hundreds or even millions of numerical dials. Also, the network makes much more specific guesses. It would say that there's a 64% chance that it's a cat, or a 32% chance that it's a dog. To build the network, there's a row of neurons on the left called the input layer. Then there's a row of neurons on the right called the output layer. All the neurons in between are called the hidden layers. They're hidden because it's not the input or output. To start, we'd feed the input layer of the network a picture of a dog. We know it's a picture of a dog because we've labeled it. But the neural network doesn't look at these labels until it makes a guess, just like the animal, vegetable, mineral game. The network would then look at each dot in the image as it passes through the hidden layers. Then it makes a guess for the output layer. Let's say for the first guess, it says there's a 10% chance the image contains a dog. Then the network compares its guess to the label on the image. This is called training the neural network. Then the network goes backwards and adjusts the neuron dials so that it can see patterns in dog photos. Then it takes another dog image and sees if it gets closer. The neural network then tunes itself by looking at hundreds of thousands of pictures of dogs. Then it will adjust its own dials until it consistently guesses correctly. Now, it's important to keep in mind that the neural network isn't seeing the dog the same way you do. It doesn't think about panting, barking, or fur. Instead, the system only sees the dog as a recognizable pattern of dots in an image. When there's dots in a dog-like pattern, then the system makes a guess. Now remember that these neural networks are still machine learning systems, so the network needs access to huge amounts of data. If you don't have hundreds of thousands of pictures of dogs, then there's no way for that artificial neural network to learn. In the end, this is the key benefit of an artificial neural network. It can train itself to understand patterns and recognize that input when looking through massive amounts of data. Over the last 30 years, machine learning systems have become the dominant form of artificial intelligence. That's because these systems are exceptionally well designed to look for patterns in massive data sets. Machine learning has also been supercharged with the wide availability of digital data. If you want to create an AI program to identify dogs, you now have access to millions of images. You can feed your network and help it learn with the large volume of available data. It's the same with other types of data. You can easily get digital video, audio, images, and documents. Just a few decades ago, it would have been extremely difficult to get even a few thousand digital images. Now it's trivial to get access to all kinds of data. Remember that machine learning systems feed on data to learn new things. The more data you feed into the network, the easier it will be for the machine to identify patterns. Think about the system that you're using right now. This is a professional social network that provides video training. users watch the training through an online video player. That video player collects data about how often you fast forward or how long you watch before moving on to the next lesson. Now suppose that the player records that data for everyone who watches the videos. That might be hundreds of thousands of videos and millions of users. So that's a lot of data. No human could look through all that data and gain any meaning from it. But machine learning algorithms look through this data and find patterns. You can see which content users find more interesting. This is exactly the type of data that many businesses have been looking for. You can now see real-time patterns in how your customer interacts with your product. In many ways, this data can tell you a huge amount, not just about your customer's interest, but even broader trends in industries. This data has an enormous amount of value. You can use it to build new customer products or to improve products you already have. It's no coincidence that companies like Google and Microsoft are most enthusiastic about AI. In many ways, their whole business has been built on using machines to interpret massive data sets. This type of pattern matching can be a huge competitive advantage. Plus, newer artificial neural networks now allow machines to find patterns in even larger data sets, when just a few decades ago, these patterns would have been imperceptible with regular machine learning algorithms. In fact, one of the largest challenges around machine learning is that humans don't really know how the machine identifies these patterns. It's like a black box of data and processing power. People simply can't process data at that same level. So if your organization is starting its own AI program, they should be comfortable with the fact that the network might be sensing things that humans are unable to perceive. This might not be a challenge with most companies, but might be a real problem with industries such as insurance and healthcare. You don't want these systems making decisions about your customers' health and safety that humans can't understand. Artificial intelligence is not the same as human intelligence. And even though we might reach the same conclusions, we're definitely not going through the same process. Think about the type of data your organization collects. Are they using the data for machine learning? If so, what kind of patterns is the machine identifying, and for what purpose? One of the best ways to connect with humans is to join us in the physical world. That's why robotics is one of the most interesting areas in artificial intelligence. Robotics is about having machines work on physical tasks. This can be lifting heavy objects in manufacturing or using robots to deliver food. Robots can even be vehicles like self-driving cars or subway trains. Inventors have long been fascinated with finding ways to have machines behave like living objects. In the past, robots were just limited to highly specialized machines. They were used as welding machines in auto manufacturing. The auto plants near my hometown employed several specialized robots. Some could lift a car and install parts underneath, but none of them would ever be mistaken as intelligent. As impressive as they were, these robots were very limited in what they could accomplish. Unless they were programmed, they couldn't help a coworker open a car door or start painting the hood. They worked best for repetitive tasks. Robotics combined with machine learning gives us many more options. A machine can adapt to its environment and learn new tasks on the job. A basic example of this is self-driving vehicles. You couldn't program a car to react to everything it might see on the road. That's why the newest vehicles are using machine learning on an artificial neural network. These vehicles are outfitted with complex sensors that feed data into the network. It needs to understand all the different roads a vehicle might encounter. Then it needs to look at all the different people, animals, and other vehicles the car might find on these roads. Then the machine looks for patterns in successful driving. A car must react differently when a deer is crossing the road than when it sees a pedestrian walking a dog. That's why you often see self-driving cars with a human in the driver's seat. They supervise how the artificial neural network reacts to the data streaming in from the outside world. But like any new skill, it takes time for the machine to collect enough data. In artificial neural networks, this is often called training the network. Google famously said that they think of their self-driving cars not as a robotics problem, but as a data problem. It's true that to figure out how to get a car to steer left or right is simple compared to having a car understand when to turn left or right. Some robots don't need this level of complexity. That's why some of them just use good old-fashioned AI. Remember that this is an AI system that uses symbolic reasoning instead of machine learning. He would just try to program the robot to act intelligently. This is the difference between a Roomba that's just programmed to avoid bumping into walls and a self-driving car that really needs to understand the roads. Most robots today are still programmed like a Roomba and not learning like a self-driving car. That's because when you're in the physical world, there's a much higher price to pay if you make a mistake. So if you wanted to create a robot that distributes prescription medication, there's a huge cost to making errors. That's why many robots take the simpler approach and still benefit from symbolic systems and good old-fashioned AI. As humans, we're always trying to do a better job communicating. So it's no surprise that we want to communicate with our machines. In many ways, machine-to-machine communication is much more accurate than human communication. Computer networking transmits exact copies of information at lightning speeds. Humans, on the other hand, are always struggling to reach greater understanding. If you can deliver 10% of what you're intending, then you're a master communicator. That means that the machines we rely on must do a better job communicating in our world. To achieve this, AI programs do something called natural language processing. This is when you interact with the machine using your own natural language. You can talk with the machine in the same way you talk with other humans. We're all familiar with communicating with a search engine like Google. There's a little box and then you type in questions. You can type something like recipe for Belgian waffles. Then the search engine will match your phrase to popular results. Now with some smart devices, instead of typing, you could say this in natural language. You could use natural language like, could you give me a good recipe for those big fluffy waffles? It's very common for humans to describe things by their attributes. In this case, good, big, and fluffy. To understand the request, the system uses natural language processing. The machine needs to understand that good is relative. So in this case, the person probably is looking for top recipes. The machine also must figure out what's a big fluffy waffle. Modern natural language processing uses machine learning and artificial neural networks. It looks through millions of conversations to identify patterns. So if it sees conversations with the word big, fluffy, and Belgian waffles, then it knows that there's a pattern between these words. That's why many companies like Google, Microsoft, and Apple offer free email, voicemail, or text. It's a way to have their artificial neural networks look through conversations to better identify patterns. But natural language processing isn't just about understanding the words, it's also understanding the context and meaning. A few years ago, one of the top Google searches was, "What is love?" Humans have written on love from the beginning of language, so there's sure to be plenty of data on the topic. At the time, Google would give you a long list of results. Some of them were about biological pairing rituals and the importance of feeling connected. This was the kind of response you'd expect from a network that's just matching keywords in a database. There was nothing natural or human about it. It was just matching keywords in the database. Natural language processing gives the machine the ability to understand the larger world. If you're typing in "what is love," then you're probably more interested in romantic notions of love, perhaps even some poetry or insights into what it's like to be in love. Now with natural language processing, the Google response is much more thoughtful. You can see lists of poems in the history of romance. But natural language processing is more than just love and waffles. Communication is at the very core of what it means to be human. That's how we organize, empathize, and understand each other. Humans would never accept the machine as intelligent if it wasn't capable of natural communication. Today, there are thermostats, doorbells, and televisions that connect with each other and the world. And there are smartwatches that check your location, and some even upload medical data. This new way of connecting is commonly called the Internet of Things. Sometimes you'll see it as IoT for short. IoT devices are objects with sensors that communicate with the outside world. They typically upload data through the internet. IoT devices are a massive new source of data. They can upload their locations, so that means that if you are wearing an IoT device, then these machine learning systems can see patterns in where you travel. They can accurately predict where you work, shop, eat, watch, and who you visit. Maybe your smartwatch will tell your thermostat when you're on the way home. IoT also allows these devices to communicate with each other. They could unlock your doors or have your computer turn on when you sit at your desk. In some ways, these new devices make it easier to create data than it is for humans to analyze. That's why many IoT companies invest heavily in AI. AI not only allows organizations to see new patterns, it also allows them to quickly react. IoT devices and artificial intelligence are a powerful combination that allow companies to create systems that predict people's behavior. My family purchased one of the earliest versions of Amazon's Alexa Home Assistant. It was a terrific and simple clock. But early on, my wife noticed that the Amazon recommendation list was becoming populated with things that were part of our conversations. We once talked about visiting a relative in Rome. Then a few days later, a travel guide to Rome popped up in our Amazon recommended list. Ring doorbells also collect data on people who walk in front of your house. The company can use machine learning for facial recognition. It can then use your doorbell to create a vast surveillance network that's sold to police departments. These departments can use this data to place people at the scene of a crime or locate people they're interested in finding. One area that has a lot of growth is IoT medical devices. You can now purchase a smartwatch that's as accurate as your doctor's electrocardiogram, or EKG. They can use the sensors to detect any health issues. Then they can upload that data to their servers. Companies like Apple look for patterns in EKG data using machine learning on a neural network. Their network can go through millions of participants. They can use this data to find patterns to accurately predict any health issues. It's certainly helpful to have machines find predictable patterns. Maybe they'll find that people are more likely to have health issues on Wednesdays. They can also see patterns that affect large groups of people. You could see something like air pollution and its effect on the city's health. In many ways, the IoT devices take the strength of machine learning in the digital world and put it in the realm of the physical world. Instead of just seeing what you're doing online, an IoT device can track your behavior offline. This has enormous potential for organizations to sell you products based on what you need and where you go. So far, you've seen that predictive AI systems can be used with natural language processing, robotics, and internet-connected devices. You can also use predictive AI to find patterns in your data. This is exactly the type of application where predictive AI does very well. You could train the system to work on a specific task. Then the system will make predictions based on limited data. That way you'll have a robot that can learn a few new things, or you could train a system on how to translate a few languages. But remember, with enough data and computing power, you might also use a generative AI system. The last few years, it seems like these systems have emerged out of nowhere. A lot of it has to do with the fact that there's now access to massive amounts of data. Plus, in the last few years, the cost of computing has gone down. This mixture of massive data sets and low-cost computing helped create a bunch of new Gen AI systems. In 2022, the company OpenAI released one of the very first public generative AI systems. It was called DALL-E 2, and it was designed to create generative AI graphics. The system searched through billions of online images. It was able to see patterns in these images and generate something completely new. Many people were shocked that the system could create photorealistic images of astronauts riding horses or cats in flying saucers. This was possible due to having access to billions of photos, plus the ability to perform extensive, inexpensive computation. A few months later, the same company released a generative AI chatbot called ChatGPT. People marveled at how the system answered questions. It was trained using machine learning on a deep learning artificial neural network. But this was different from a predictive system. It was flexible, and it could answer very general questions. That's because it trained on trillions of connections between words. It gathered all the information that it could find online. It looked through the text of books, social media posts, news sites, and informational sites like Reddit. It looked through so much more data than what you'd get from a traditional predictive AI chatbot. In fact, it's still being disputed whether it could legally look through all this information. Once the system was trained, humans spent time practicing with the chatbot. Since it was gathering data from everyday people, there was a lot of misinformation. These humans helped correct the system to keep it from repeating things such as obvious errors or hate speech. The generative AI system was able to have a conversation by predicting each word in a sentence. It would respond one word at a time by analyzing billions of conversations. It could create new content by identifying patterns in the characteristics of everyday items. If you wanted to create a song about peanut butter and jelly, it would understand that jelly is fruity and sweet, while peanut butter can be smooth or crunchy. Because these systems need a lot of data and computing power, they've mainly been run by large companies. These dozen or so companies have gotten a huge head start in developing generative AI systems. So it's likely that most businesses will use these systems as a service. They'll tap into the power of their Gen AI without the challenge of building a massive system. When you think about machine learning, the key is to focus on the term learning. What does it mean for your machine to learn? What strategies can you use to learn something new? How can you take the strategies and apply them to machines? Imagine you wanted to learn how to play chess. You could do this a couple of different ways. You could hire a chess tutor, and they would introduce you to some of the different chess pieces. Then they'd show you how to move them around the board. You could practice by playing against your tutor. Then they would supervise your moves and help you when you made a mistake. If you couldn't find a tutor, you could also go to public parks. There you'd watch people play. You couldn't ask them questions, you'd just quietly watch and learn. You'd have to figure out chess just by watching the games on your own. If you did this long enough, you'd probably understand the game. You might not know the names of the chess pieces, but you'd understand the moves and strategies after hundreds of hours of observation. These two strategies are very similar to how a machine learns. The system could do something called supervised learning. Here, a data scientist acts like a tutor for the machine. They show the machine the correct answers and then let the system train itself to get better at the game. The system could also do unsupervised learning. Here you just have the machine make all the observations on its own. The system might not know all the different names and labels, but it'll figure out their way to learn from the data. As you can imagine, these two approaches have their own strengths and weaknesses. For supervised learning, the system needs to have a knowledgeable tutor. There must be someone that knows a lot about chess that can show the system how to play the game. With unsupervised learning, the system needs to have access to a lot of data. That's the only way to see the patterns. The system might not be able to go to a public park and watch hundreds of people play. It also depends a little bit on who it watches. You need it to watch people who are good players. As you can imagine, these techniques are used for much more than just playing chess. Companies use these techniques to get valuable insights about their customer. With supervised learning, a company like Amazon might identify 1,000 customers who spend a lot of time shopping on their website. The company can then label these customers as high spenders. Then it would have the machine learning system look through the customer to find patterns that make them high spenders. Now, for unsupervised learning, a machine learning system could be given access to all of Amazon's customer data. Here, the system might find its own patterns in the data. Maybe somebody who buys chessboards are much more likely to buy an expensive kitchen appliance. Then Amazon could use that data to advertise. If you use Amazon, you may have noticed that sometimes they advertise products that seem completely unrelated to what you're looking for, but it's still something you're interested in buying. Both techniques have their own strengths, and yet each one can give you incredibly useful insights. If you've ever worked as a product manager or a software developer, then you know that applications need very explicit instructions. Every time you open Microsoft Windows or open an app on your iPhone, you're benefiting from a programmer coding the input and output. But we've seen that this type of programming doesn't work well with artificial intelligence. There's too many combinations to tie every input to an output. In these cases, you need a programming model that allows the machine to learn. You also must give the machine some ability to respond to feedback. Imagine you're creating a program that detects spam messages. These messages are filled with unwanted advertisements or viruses. You could easily program a word filter that deletes messages with common spam words. If you frequently get messages on entering contests, you can filter words like gold, lottery, or winner. So you can program that if the message contains gold, then treat the message as spam. But complex challenges don't work well when you're limited to programmed instructions. That's why machine learning switches this around. Instead of inputting instructions, you're inputting data. Instead of a program response, you let the machine learn from the patterns it identifies. You can start with supervised machine learning. Here you need to split your data into a training set and a test set. The training data is a smaller chunk of data that the machine uses to learn. The system will use machine learning algorithms. These algorithms rely on statistics. You'll see a bunch of these machine learning algorithms later on. These algorithms help the machine find relationships within the data. So the machine uses an algorithm that if the email message contains the word lucky, winner, or congratulations, then it's 50% more likely to be spam. Then once the algorithm is accurate enough, you can use what the system learned on a larger test data set. This test data is usually many times larger than the data that the machine used to train. Let's think about how machine learning might work with our spam detection program. We'll set aside 10,000 email messages for our training set. We'll use it to build our model. This training data has 9,000 regular messages and 1,000 messages labeled as spam. We'll also set aside 1 million messages for our test data. This test data is unlabeled. That means that it's unlike our training set, no one has correctly labeled any of the messages as spam. That would be a lot of work for 1 million messages. Your training data is then used to let the machine identify the spam messages. Then once the machine learning algorithm gets close to identifying the 1,000 spam messages, you'll try it on the larger test data set. Once you're satisfied, that will be your initial data model. Now this machine learning algorithm only has two options. Is that a regular message or a spam message? That's why this is called a binary classification challenge. You'll only need to classify your email message into one or two groups. This is one of the most common uses for machine learning. The key thing to remember is that machine learning algorithms use statistics to find patterns in your data. Once your machine identifies these patterns, it can then classify your data based on what it's learned. If you work with a machine learning team, one phrase you'll hear is we're working to improve the data model. In fact, these teams usually put a very high priority on working to improve the data model. So what is a data model? The best way to think of a data model is an abstraction of what the AI system learned from all that training and data. That's why the data model is never finished. A good machine learning team will push their model to become more accurate. So if it's 99% accurate, the team will push it to become 99.9% accurate, then 99.999% accurate. The system needs to continue to learn until it almost always guesses correctly. It might sound strange, but you also use data models. When you get behind the wheel of a friend's car, you know how to start the engine, even though you've never driven the car before. If you see a bird in the sky, you'll recognize it as a bird, even if you've never seen the species before. That's because throughout your life, you've created data models to help you understand the world. You've taken a lot of data and then you have extracted it down to core concepts. That way you can apply these concepts to something new. The more data you've processed, the more accurate you'll be at making guesses. So if you've seen thousands of species of birds, there's a pretty good chance that you'll guess the correct species. The more cars you've driven, the better you'll be at driving a new car. In a sense, your data model is what you've learned from all that training and data. Data models are important to understand when comparing predictive and generative artificial intelligence. Data models are mostly used for predictive AI. In fact, most of the machine learning algorithms that you'll see later are used for data models. So you'll only use them to make predictions. That's because predictive systems are trying to get better at making specific guesses. You'll be creating a data model to understand that one data set. It's the same way that you would use a different data model to drive a car than you would use to identify a bird. Each of these requires training on a different model. So if you drive a lot of cars, you won't be any better at identifying birds. You need to train yourself on bird species, but that won't help you be a better driver. But remember that generative AI is much more flexible, but it also needs more data. Think about if you ask a generative AI chatbot a complex question. Like you ask it to write a story about you driving in a sports car with Big Bird from the show Sesame Street. The Gen AI system needs to know a lot about birds, cars, roads, and even television to be able to generate that story. Data models are still the core of AI in most organizations. That's because predictive AI gives you a lot of power, but not a lot of flexibility. Later, you'll see a lot more flexible model that you can use for newer generative artificial intelligence. As humans, we classify things all the time. We put our Microsoft Word docs into folders. We separate our business contacts from our personal contacts. We list out things alphabetically. Without these classifications, we'd have a hard time organizing the data. Businesses need to organize the data the same way. Airline companies want to classify their customers by frequent flyers. Retailers want to classify their highest spenders. Search engines want to classify the likelihood you'll buy something online. Binary classification is one of the most popular supervised machine learning challenges. That's because it's simple and it's powerful. With binary classification, there are only two possible outcomes. Is the hotel room going to be booked next week? Will the stock market go up this afternoon? Is this email message spam? All binary classification uses supervised machine learning. Remember that supervised learning depends on labeled data. That means that the machine learning system is trained to classify the two answers. So to use these systems, you need to first create a training data set. Credit card fraud detection systems are one of the most popular ways to use binary classification. Every time you use your credit card, a machine learning algorithm classifies your transaction as fraud or not fraud. Since this is supervised machine learning, the credit card companies had to start out with tens of thousands of examples of fraudulent transactions. The data science team would train the system on how to recognize the patterns in future transactions. Email providers use supervised machine learning to classify spam messages. They start with a labeled training set of messages marked as spam. Once the network processes enough messages, it'll classify your spam email. These techniques are inputting massive amounts of data and then using machine learning algorithms to classify your data into human-created categories. Categories like booking data, fraudulent transactions, and unwanted email. A data scientist creates these categories, and then your AI system classifies the data that it's been trained to recognize. Now, classification is one of the most popular forms of machine learning, but it also takes a lot of upfront effort to train the system. It can be a challenge to get tens of thousands of fraudulent credit card transactions or tens of thousands of spam email messages. Plus, there's no guarantee that'll be enough for the system to make accurate predictions. That means your data science team might find itself going back and getting another 10,000 transactions. Your team will have to feed the machine learning algorithm until it's extremely accurate at classifying your data. That's why even now, after several years of development, your credit card company might send you a fraud warning, even though it's not a fraudulent transaction. Data scientists are constantly training these systems to make the classifications more accurate. credit card fraud, spam detection, and online purchasing might all seem like very different challenges. But to your machine learning system, they're all just different ways of doing the same thing. You're classifying your labeled data into predefined categories.